This video discusses the paper Predictability Awareness for Efficient and Robust Multi-Agent Coordination, presented at the AAMAS 2025 conference. I'm Roman, and I had the pleasure of authoring this paper with my collaborators Khaled, Daniel, and Javier. So, diving in, recent robotics advancements have enabled autonomous systems like Waymo's Level 4 robotaxis to operate fully autonomously in uncontrolled environments. However, a critical challenge persists, and that is planning safe trajectories in unstructured interactive settings where agents mutually influence each other through a complex mix of rational and stochastic behaviors. Effective coordination requires agents to reason about each other. However, this introduces substantial uncertainty in estimating other agents' objectives, as well as a computational complexity that grows exponentially with the number of agents. The literature for interactive planning can roughly be categorized into two approaches. Joint trajectory optimization approaches formulate a single, large-scale, multi-agent planning problem, sometimes also referred to as a trajectory game. We explicitly model each agent's cost function and solve for a Nash equilibrium or Pareto optimal solution. Although this often results in stable and coordinated interactions, as a result of this combinatorial formulation, the computational complexity grows exponentially with the number of agents. On the other hand, sequential predict and plan decouples prediction from planning. We would first predict others' trajectories, and then plan a trajectory for the ego that avoids collisions. This approach has the benefit of scalability, but in highly interactive environments, it often fails. The two main reasons are that these environments are intrinsically chaotic and hard to accurately predict, and second, agents are unaware of how their plans will influence the quality of their predictions. Given this context, our goal is to develop a method capable of achieving coordination quality approaching that of joint optimization while retaining a scalable, sequential architecture. We can now look into the shortcomings of sequential approaches in a bit more detail. In a typical sequential setup, the prediction module outputs what others are most likely to do. And then, in the planning module, using this information, the only mission is to find the most cost-efficient path that avoids collision. The problem is that this overlooks that other agents also hold beliefs about us. If our individually optimal trajectory doesn't align with their expectations, they'll be surprised and might have to adjust their path. This in turn may surprise the ego agent in return, forcing it to also react. These reciprocal reactions can cause a chain effect, leading to a breakdown in coordination. This breakdown manifests as jerky trajectories, high control effort, or in the worst case, collisions or deadlocks. To illustrate this, consider a task where agents have to exchange positions with the opposite agent. Here, agents are equipped with a fully informed, near-perfect prediction model. Despite receiving optimal joint actions as predictions, agents are unable to use this information to coordinate. Agents display selfish deviations from this optimal joint action, leading to a breakdown in coordination. The video shows this clearly. Agents continuously surprise each other and have to adjust their paths. This is visible through the constantly changing trajectory geometries. The key takeaway from this is that even with a very high quality prediction model, sequential predict and plan agents may fail to coordinate in dense interactive scenarios. To address this problem, we propose to introduce predictability as a planning objective, where in addition to minimizing its intrinsic cost, the agents balance this with minimizing the surprise it induces in others by remaining predictable from their perspective. However, this requires modeling other agents' expectations. We do this by allowing agents to predict themselves. So we can think of prediction models essentially as a kind of soft social norm or convention. These models learn to encode the typical or most likely outcome for a given scene. By predicting itself, these ego predictions then represent the beliefs other agents have about the ego agent. This information can be used in planning to introduce a penalty for trajectories other agents will find surprising, bringing the optimal trajectory closer to the expectations surrounding agents' hold. This approach then ensures that the agent's behavior is not only goal-directed, but also aligned with maintaining coherent and accurate beliefs about the surrounding agents. As an illustration of this process, we can bring back the example scenario from before, but this time we account for predictability. Now, when agents nudge their behavior to align with others' expectations, instead of surprising, they are reinforcing other agents' beliefs about them. This, in turn, also makes other agents seem more predictable from the ego agent's perspective. Through this process, We have effectively aligned individual incentives such that by greedy individual optimization, coordination emerges at the group level, with the decision about what coordination strategy is eventually executed now being relegated to the prediction model. To conclude, our work shows that by accounting for predictability, we can achieve coordination quality approaching that of joint optimization while retaining a scalable, sequential architecture. Furthermore, by accounting for predictability, agents close the loop on prediction errors, making prediction models appear more accurate and enabling effective coordination even with simple, easier-to-train models. Finally, our approach helps autonomous agents better approximate human driving patterns when using human data-trained prediction models, facilitating smoother integration into human-populated environments. If you're interested in our work, please visit our website by following this QR code. Here, you can find a PDF of the paper, videos of more results, and the code to replicate our experiments. Thank you for your attention.